This is AQA GCSE Chemistry. It's a dual award and triple award topic, and this is an introduction to the topic electrolysis. So we are going to build on this in future videos, but this gives us a very gentle introduction. So as always, I'm going to recommend that you pause, have a go for yourself before reviewing the answers. So in this particular video, we're going to look at what happens in electrolysis, know what type of substances can be electrolyzed, and identify what the product of electrolysis of those compounds would be. There's a definition provided. It's a really important definition to learn and to understand. And we also need to relate this back to the bonding topic that was covered way back in chapter 3, C3. Electrolysis will only occur in ionic compounds, and it will only be in certain circumstances with those ionic compounds. What will those circumstances be? And what we're looking for is that there needs to be the opportunity for electricity to flow, and the only time that can happen in ionic compounds is when they are aqueous or molten. Moving on. And we have got here the electrolysis of zinc chloride. Now, there are videos out there for you to actually watch that elsewhere. I'm going to focus here on what you would do to draw the diagram of it. So have a go, see how you do. The key thing with any diagram within chemistry is to keep it simple. And you can see here that I've drawn a vessel, I've got something in it, I've got an electrical circuit, and I've got these two parts of the circuit extending in there. I've also got heat down here. I need to heat for reasons I will come to in a moment, but I am going to show that I'm not going to draw a Bunsen burner. I actually need to show what each of these things are. I need to label it. So this is a crucible, and this is the molten zinc chloride. I've put zinc chloride in the crucible, I've heated it, so it's become a liquid. I don't need to label the electrical circuit because these are standard symbols for a cell and for wires. But I can label my positive and negative electrodes. My positive electrode is connected on this side, and the positive electrode is the anode, and the negative electrode on the other side is the cathode. In summary, remember that with any diagram that you draw in chemistry, it needs to be two-dimensional, it needs to be cross-sectional, and it needs to be fully labelled. We're going to stick with zinc chloride. Remember that electrolysis will break down an ionic compound into its elements in their standard states at standard conditions. So it's zinc chloride is going to break down into zinc and chlorine. So my equation here is going to represent that. ZnCl2 breaks down to make Zn, that's solid, and Cl2 gaseous. We're going to talk in later videos about what actually happens to get there, because clearly this contains zinc ions and chloride ions. But at the moment we're just dealing with the basics. You do have to remember chlorine is a diatomic molecule. Chlorine exists in pairs. If you forget that, you're going to lose marks in this particular question. So let's do some more examples of this. Let's break down iron bromide into its elements. And on this one, we've got FeBr2. Once again, that's liquid. We're going to break down into iron and bromine. Fe is going to be solid because that's how it exists at standard conditions. And again, just like chlorine, bromine is a diatomic molecule. It exists in pairs. Bromine is also one of very few elements that are liquid at room temperature, so the state symbol should reflect that. Let's try another one. Copper and oxygen. Copper oxide. We know we're going to break this down into copper and oxygen. Starting with liquid copper oxide, the copper is solid, and oxygen is another example of an element that's diatomic. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, astatine are the diatomic molecules. Have a look at them on the periodic table to see the pattern that's going to help you to remember that. Alternatively, you can remember H-Noth Culbriat, and that's all of the symbols of the diatomic molecules together. But because I've got one oxygen on the left, I only need half an O2 on the right. The alternative would be to put a 2 in front of the CuO and a 2 in front of the Cu. That would balance it in exactly the same way. And then let's have a look at another example. And here we're going to break lead bromide down into lead and bromine. We already know that bromine is diatomic. We already know that bromine is a liquid. We spoke about that earlier. So PbBr2 liquid goes to solid Pb and liquid Br2. Now we're still building up to an understanding of electrolysis, but let's take a look at what we have here, because to make my zinc and chlorine, going back to that first example, I am going to need to break down an ionic compound. And as I've already touched on earlier in the video, zinc chloride is made of zinc ions and chloride ions. Now, you are expected to remember the charges on common ions, but there are ways that you can help yourself to remember that. Chlorine is in group 7. Group 7 will always form ions with a -1 charge. That means that my Cl minuses, if I've got 2 of them, my zinc must be +2 to balance that out, because the overall charge on a molecule or on an ionic compound is 0. So we're going to do the same with 3 more examples. I've got copper bromide, lead chloride, and copper oxide. What will be the charges on the ions that make them up? Well, we've already touched on the fact that group 7 form ions with a -1 charge, so I can put my -1 and -1 in. Oxygen is in group 6. In group 6, to form an ion, you will gain 2 electrons to form a full outer shell. That means that group 6, we have a charge of -2 on the ions. And from there, we can work out the charges on the metals that they are bonded with. If oxygen is -2 in CuO, the copper must be +2. In the remaining 2, for CuBr2, I've got 2 Br minuses. In PbCl2, I've got 2 Cl minuses. So for that reason, the copper must be +2 and the lead must be +2. What we're actually looking at here is the reverse of what we did when we worked out the formulae of ionic compounds way back in the bonding topic, chapter 3. That takes us to the end of this video. Thank you for listening and goodbye.